Hello, everyone. I'm Haichen Shen. I'm glad here today to talk about the scroll design and architectures and how we transform the zk EVM circuits into a layer 2 zk-Rollup layer 2s. Okay, next page. So for those who haven't heard about the scroll, and then let me just use one single sentence to summarize what scroll is building. Next page. So the scroll is building a general purpose EVM-equivalent zk-Rollup layer 2 chains to scale the Ethereum. So that's a very simple, straightforward. And before I dive into any technical details, let me first describe the principles that in the back to guide our design decisions. So first and foremost, we believe that ensuring the user security should always come first. So in scroll, that means all of the layer 2 transactions should share the same security level as the base layer, the Ethereum layer, even without trusting any layer 2 operators. And then we should never trade off any the user security for any other properties. And second, maintaining an effective Ethereum scaling solutions should give users and developers a seamless migration path from the existing dApps and the developer toolings. And we believe that maintaining the EVM equivalence is the best way to achieve this property. And third, as Justin previously talked a lot about the censorship, decentralization is one of the key properties to achieve the censorship resistant. And we believe this is also one of the key properties we should achieve, and then even in the layer 2 context. And then this decentralization can help the protocols, ensure the protocol to be resistant to any censorships or coordinate attacks. And inside the scroll, we consider all aspects of decentralization across all layers, including the sequencers, provers, and then the community of the users and developers. And then fourth, for a user on a layer 2 to achieve a great user experience on the layer 2, we believe there are two key properties we need to achieve. First, the transaction fee should be low, and then orders of magnitude lower than the base layers, the Ethereum. And then second, the users on the layer 2 should experience instant pre-confirmations on the layer 2 transactions and a reasonably fast finality time on the settlement layers. To achieve these two properties, you also need to achieve very great efficiency when designing the zk-Rollup layer 2 chains. Okay, next. And then let's take a look at see how the design principles guide our design decisions. First, the user security and the EVM equivalence lead to a zk-EVM-based zk-Rollup solutions. So first, people already know that zk-Rollup is secure as it be guaranteed by the mass and the zero-knowledge protocols behind that. And then the zk-EVM is the holy grail inside the zk-Rollup, as it maintains the EVM equivalence as well as achieving the same security from the zk-Rollup and the zero-knowledge proof protocols. And then second, the decentralization principle leads us to design a decentralized prover networks. When we're designing the zk EVM circuits, we quickly realized that putting the EVM into a zk proof will result in a large overhead because of the incompatibility of the base fields. So that leads us to design a decentralized and permissionless prover networks that can help generate the zk proofs and scale up. So there are two key benefits from having a decentralized prover networks. First, we design and build our proving infrastructure to be highly scalable, so that we can easily scale up the proving powers by including more proving nodes in the network. And the second, the community will be incentivized to build a more substantially better and more effective hardware and software solutions. And then they can run the proving node themselves instead of relying on the scroll to running all of the provings in the centralized ways. Okay, next slide. And then third, the efficiencies. So we focus on, we believe that to achieve better efficiencies, we need to leverage a lot of innovative research-driven solutions from all of the communities. Our zk EVM designs leverage and takes advantage of a lot of recent breakthroughs inside the zero-knowledge proof systems, the proof aggregations, and the zk hardware accelerators. And we also build in an open source community, in an open source way, like our circuits and then things like has been open source from the day one. And then this allows us to be built with our open source community, including the PSC team from the Ethereum Foundations and other open source community contributors. And I believe like with the discussion and then the collaboration with all of the open source community, we can find and build the best and the most efficient solutions for the zk EVM and the zk-Rollup chains. Okay, now let's take a look at the scroll architectures. So it involves two layers. One is the layer 1, which is the layer, and the second is the layer 2, our scroll chains. So in this layer 1 Ethereum, we'll mainly deploy two contracts. One is the bridge contract for bridging any assets between the layer 1 and layer 2, and for other general purpose messages. And second is the Rollup contract that's going to record any data availability from the layer 2 chains, as well as the zk proof and verify that. And in the layer 2, we have the scroll node, which is going to be responsible for accepting, processing the layer 2 transactions, generating layer 2 blocks, as well as like the accepting RPC calls. So if you take a look at it closer to the scroll node, there are 3 modules in total: the sequencer, the relayer, and the coordinator. And the sequencer is basically the key component inside the scroll node. That's basically it processes the layer 2 transactions, access RPC requests calls, and then generates the layer 2 blocks. Our sequencer implementation is based on a fork of the Go Ethereum, which is one of the most popular and commonly used execution client for the Ethereum. And then, but we made some tweaks of the Go Ethereum to adapt for the layer 2 purpose. And then by directly forking the Go Ethereum implementation, we believe that it can achieve the best compatibility and for all of the with the Ethereum, as well as like all of the RPC interfaces. And next, the relayer is going to be basically it's responsible for relaying any tokens and message between layer 1 and layer 2 by watching those any logs and events from the bridge contract. The relayer will also upload any data from the layer 2 blocks and then to the Rollup contracts, as well as roll up the zk proofs into the Rollup contracts as well. Okay, next. And then third module, the coordinator. The coordinator received an execution trace from the sequencer once like every new block is generated. And then it can dispatch this execution trace to the rollers, which basically we call like the rollers are the provers for the zk proof generations. And those rollers are utilizing, basically the rollers is running the zk EVM in behind to generate the validity proof to prove the correctness of all of the transaction has happened executed in the layer 2s. And we expect that the rollers to be running on the hardware accelerators. Our current implementation uses GPU provers to speed up the proof generations. But we expect that the community in the future can come up with better either like software solutions or better hardware to further reduce the proof generation time and reduce the cost to generate a zk proof. And all of the rollers will construct a decentralized prover networks and will be run and then managed by a community, not only by the scroll team. And then if we take a closer look at what happens inside the rollers, actually it's more complicated than just running the zk EVM circuit. So first, the roller will receive the execution trace generated by the sequencer. So the execution trace includes a few things. First, it has the execution steps, like step by step, what opcodes you executed when you're executing these transactions. And the second, it will have the block headers and then the transaction data that are going to be needed for to generate the zk proof. It will also include the contract bytecode to make sure like the bytecode you executed will be correctly verified inside the zk EVM proofs. As well as like there will be the Merkle proofs that are going to use to prove any state transition from the old state root to the new state root. And then next, the execution trace will be passed into the circuit input builder. But it's going to transform all of the information included inside the execution trace into a giant circuit, the witness into the circuit. And it will be like expanded the data a lot, because when you're trying to prove that, you also need to generate a lot of auxiliary data and to fit into the witness of the circuits. And then when we talk about the zk EVM, actually it's not consists only single circuit, but it comes with a set of circuits. So for example, I listed here like the EVM circuit, which is the core circuit inside the zk EVM. That is going to prove the state transition of the virtual machine, of the Ethereum virtual machines. And it will execute like the opcode by opcode. But I won't go like much details into the EVM circuit and other circuits in this talk. And then second, the RAM circuit is going to be responsible to constrain any read-write operations that happens inside the Ethereum virtual machine. For example, any stack pops and pushes, and the memory read and write, and any storage changes. And then third, the storage circuit is going to prove the state root transitions. Basically, you're proving the Merkle tree that translates from the old state root to the new state root by applying all of the storage changes to all of the account trees and then the storage trees inside each contract account. And there'll be a few auxiliary circuits that are going to help the EVM circuit to prove some complicated opcodes, such as the SHA-3, the catch functions. And then all of these circuits will be generating a single, each circuit will generate proofs. If you're just uploading all of the proofs immediately to the layer 1 Rollup contract, then we're resulting in a much more overhead in terms of the cost and then the gas cost on the Ethereum. So in order to reduce this overhead of multiple proofs from those set of the circuits, we further apply an aggregation circuit. That's basically mimic the verification logic happened inside the verifier of those proofs. And then you can aggregate this multiple proofs from the zk-EVM into an aggregation proof. Yeah, and then we call this aggregation proof because this is execution trace is for a single block, so we call this like a block proof. And then this is like what happens inside a single roller. And then you can expect like the proof generation, the whole proof generation process will take longer time than a block generation time. So you can expect there will be multiple rollers that are going to execute and generate this block proof for different blocks in parallel. And then to further reduce the overhead of the verification cost on the layer 1, so we can then apply another layer of aggregations. So basically, you can aggregate these multiple block proofs using the same aggregation circuit and then into an aggregation proof. That will be like the final proof, which will be roll up into the layer 1 Ethereum chains. OK, now let's put in this everything together and then see how the zk-Rollup work in the actions in this timeline graph. So first, the sequencer inside the scroll node was going to generate the layer 2 blocks. And then once like a block is proposed by the sequencer, we just call it a pre-committed block. So the pre-committed just means that the block is being proposed by the sequencer and then included in the layer 2 chains. But it's not a canonical part of the scroll layer 2 because there's nothing like that no block information has been posted to the Ethereum. But user can still act on top of those pre-committed blocks in anticipation, like if the user trusted the sequencers in the layer 2. And then once the layer 2 block has been generated, so we'll extract some certain information from the block headers and the transaction data and upload them into the layer 1 Rollup contracts for the data availability. And then once that data availability, once that the transaction has been confirmed on the layer 1 for the data availability, then the block status transits from the pre-committed to the committed blocks. So here, the committed means that a block data has been already uploaded to the layer 1s, and then you cannot any modify those of the data on the layer 2s. And then what happens the next is that you will also meanwhile you also extract the execution trace from this layer 2 blocks and send to the coordinator, which then forward this piece of trace into one of the idle rollers for the zk proof generations to generate the block proof. And then you can see there will be multiple blocks happen in parallel, and then the proof generation will be run on different provers on different rollers, so on and so forth. And then after a while, if the proof generation has been already generated by the rollers and reply to the coordinators, the coordinator is going to batch a few block proofs together and then issue another special request to another rollers going to generate the aggregate proof generations, run the aggregate proof generations that are going to aggregate multiple block proofs into a single aggregation proof. Yeah, and then that aggregation proof will be replied back to the coordinator, and then that will be going to submit it to the layer 1 for verifications. And notice that all of the previous data the data that has been rolled up in the Rollup contract will be also the input to this verification contract going to verify the data that's previously uploaded to layer 1, as well as the aggregation proof to the aggregation proof of these blocks. And then once that transaction has been correctly executed and confirmed, then we can translate those blocks that be included inside this aggregation proof as the finalized blocks. And this, like the finalized blocks, that means like it has been a canonical part of the scroll layer 2s and have already been, you have access to the data of those blocks, and as well as like those blocks has been secured and verified by a zk proof. Okay. Yeah. Okay. So that's like about everything about like our architecture and then the designs. So we have been running this pre-alpha testnet of everything like we mentioned before for like about like over a month. And our pre-alpha testnet consists two parts. The one is the scroll layer 1, which is a fork of the Ethereum utilizing the proof of authority-based consensus. And then scroll layer 2, which is a zero-knowledge based Rollup testnet deployed on top of the scroll layer 1. And then on top of this testnet, we provide a few pre-deployed demo applications, including the faucet on the layer 1 that are going to issue the test tokens for the users to play with our testnet. And then the bridge that are going to transfer the tokens between the scroll layer 1 and the scroll layer 2. And then a swap as basically a fork of the Uniswap v2 deployed on the layer 2 for swap the tokens or provide liquidities. And then we are also going to generate all of the data availability. We'll roll up the data availability to the scroll layer 1s, as well as like generating the zero-knowledge proof, the validity proof on the fly. And then you can see like all of the blocks, the state of the blocks, we're going to transit from the pre-committed to committed, and then finally like going to be finalized by the validity proof inside this Rollup Explorer. And then to become an early tester and contributors, you can sign up at our signup.scroll.io. Okay. Yeah, and we're also like letting more and more users and testers into our testnet for that. Okay, so previously it's all about the scroll, and then so the next few minutes I'm going to talk about the Ethereum roadmap and how the Ethereum roadmap is going to impact the scroll as well as like other layer 2s in general. So everybody know like on the graph on the right is the roadmap like the Ethereum Foundation has put for the roadmap, and then we know like the merge is coming very soon, like in about 2 weeks, and then there comes like a follow with the surge, and then with the dank sharding, and then the verge, and then the plurge, and then the spurge, and they have everything to that. So first of all, like, for the proof of stakes and then the merge, it doesn't have an immediate impact to the layer 2s, but it's very great for the Ethereum to achieve better energy efficiency, like to be more eco-friendly. But it's also like important stepstones for the incoming dank shardings, which has greatly reduced the Rollup cost for the layer 2s. And then like I'm also going to talk about the end goals, which like very ambitious goal from the Ethereum for the Ethereum is going to zk stunk everything. So what happens after this proto dank sharding, like which comes like earlier, and then we'll have the dank shardings, is that it has a new type of the transaction called blob transactions, where then after this like the proto dank sharding, now you can put a lot of data of the layer 2 transaction data into these blobs, like which is going to be very cheaply stored on the under those like the storage shardings. And then inside of the real core data, which is going to be accessed by the smart contract in the layer 1, is only to be like a few simple things, including the pre-state root, the post-state root, and then the zk proof or the KZH commitment. And then using those very like succinct information, then you can make sure like still use all of the transaction data, like and guarantee that the data will be stored on the Ethereums for the data availabilities. So with this like the proto dank shardings, you can greatly reduce the cost of the layer 2 to roll up any transactions to the layer 1s. Because currently, like, even though like if you want to verify a zero-knowledge proof on the layer 1, it's still like compared to the data availability. So the data availability still takes the most significant part of the cost for the layer 2s. And then not only so we also know this proto-dank sharding and dank shardings. So with the dank sharding, you can have further a better use for data per blocks, meaning you can put more data into the after you have the dank shardings, and also because it can reduce a lot of for the data availability than bandwidth. So that means you can scale up more transactions. So currently, if you're talking about layer 2s, you can probably think of a limit of 2,000 transactions per second on the layer 2s. But with the proto-dank sharding or dank sharding, it could be the 1 to 2 order of magnitudes, the higher than the current estimation of the layer 2 throughputs. Okay. So last, I was going to talk about the end goal of the Ethereum, going to zk snark everything. So first, a very exciting topic is going to say if we can integrate the zk EVM in the base layer. So this will require the zk EVM will be exact achieve the exact semantics or all of the specs as the current Ethereum virtual machine does. And then second, if you want to include the zk EVM inside the base layers, basically you need to achieve a reasonable efficiencies. You cannot wait significantly delay the confirmation, the finality of layer 1 blocks. So you need to still combining the new breakthrough and the innovations in the cryptography for greater efficiency and simplicities. And the third is so people are thinking also from Ethereum is the zk snark everything. That means there is not only the zk snark, the execution client is also means that you can also zk snark the consensus layers by doing some zk attestations. So it'll be the zk snark everything. And then finally, I think the final step we're trying to upgrade for the quantum resistance, the post-quantum safetyness, for using the new protocols the zk protocols. And then we Scroll will be very open and we'll be very glad to contribute to any things on the Ethereum roadmaps, and then trying to see if we can help contribute to all of things in the open source communities. Okay, thank you. And then just remember you can sign up on our pre-alpha testnet at signup.scope.io. And thank you very much.
Thank you. Thank you, Haichen.